Hello, we are Team Gold, and this is Project 2. In this project, the task we are given is to create one of the 6 buckles on a 6-point harness with specific forces and dimensions in mind. There are many potential design variations that one can make, but the main focus should be that the buckle can withstand the forces that act on it, so it does not fail. A high emphasis on safety factor is important because that is one of the key components that makes sure the race car driver is not ejected from their car in the event of a crash. The outcomes for this project are solving for stress concentration factors through hand calculations and estimating the location of maximum stress, using FEA software to calculate what and where the location for the maximum volume usage stresses are at, and a fully designed buckle that is light in weight yet can meet the proper safety factor for the design requirements. In order to fully understand the principles of the maximum stress location, it is more simplistic to separate the buckle by subsections for visualization purposes as well as solving for hand calculations. Each buckle has evenly distributed force from the driver. For the FEA analysis, the bolt hole is considered static. We assume that most of the stress will be located around the bolt hole, the slot for the strap, and the fillet. Here are figures 1, 2, and 3. From these locations, we believe that the maximum stress will be located in the slot for the strap. This is since the rectangular shape in figure 2 lacks the ability to reduce the stress concentrated in that area. The factor of safety that our buckle needs to meet is 1.5. And in the model, our knowns are the size of the slot, the bolt diameter, the thickness of the buckle, and the force acting on it. The unknown variables for the buckle are the volume usage stresses, the points of interest, the geometry, and the max stress on the buckle.
We use the charts of theoretical stress to go ahead and find the concentration factors, which in this case is KT. For the strap slot, which is the section on the top, mention it right here when it says for the section, we calculated that KT is equal to 6.28. We went ahead and calculated the area for this section, and after that we calculated the stress, which is force divided by area. To calculate the mass stress, it is KT, or the concentration factor, times the stress on the area. We calculated that that was 577.52 megapascals. For the bottom section, we used the play with the circular symmetric hole charts of theoretical stress to calculate KT. This gave us a KT of 2.43. We went ahead and calculated also the area and the stress. Using this, we went ahead and calculated that this is 148.98 megapascals. This is less than the one that we had before, meaning that this one will be under less stress and will be less likely to go ahead and fail. For the top section, we use the rectangular bar with a single fillet charts of theoretical stress to calculate KT. That gave us a 2.59. We went ahead and calculated the area for this also and the stress, giving us a max stress of 198.48 megapascals. This is a bit less than the one that we had before, but it is even less than the one that we had first, so meaning that this will be less likely to break. Here you can go ahead and see a couple of the calculations that we did. For example, we calculated the stress going on the buckle. That gave us 14.8832 kilonewtons. You can also see how we calculated KT, which is the max stress divided by the stress going on the buckle. So according to the graph before, we said that the max stress is going to be 577.52 megapascals. And how this is less than the max stress or the ultimate stress given, which is 950 megapascals, we know that there's going to be no failure. To calculate the factor of safety, we know that the formula is ultimate stress divided by the actual stress. So the ultimate stress will be the stress at 950 megapascals, and this will be divided by the stress, the max stress that the buckle will be going through. That is 577.52 megapascals. Dividing this, we have that the safety factor is 1.64.
To determine the weight of the buckle, we decided to make a free body diagram of the buckle itself and dividing it into parts. We divided it into 8 parts as listed in this slide. Taking the volume of each of these components 1 through 8, we were able to determine that the total volume of the buckle was 0.984 inches cubed. Knowing that the density of the material, titanium 64IA, we know that its density is 0.16 pounds per inches cubed. Using the formula to find mass using D equals M over V, which is density equals mass over volume, we found out that our mass is 0.0048 plus or minus 0.005 slugs. Using the slugs, we multiplied it by 32.2, which is the force of gravity in English units. We were able to determine that the weight is 0.157 plus or minus 0.017 pounds. In comparison to the one we were calculated by SolidWorks, the actual weight was 0.139 pounds and the mass was 0.00432 slugs.
The following displays the FEA finalized CAD of our buckle. It displays the areas of interest with regards to locations experiencing stress. This simulation was utilized to compare teams and calculations for validation of our work. It also shows where and why we had stored material for optimized buckle. Here, the loads and constraints of our prototype are observed. Figure A shows where we statically constrain the bolt holding the simulation while the external tensile loading is occurring. Figure B shows the location of the initial force applied and its orientation. The greater amount of elements we have, the more accurate we are making the stress distribution in our buckle. The variation between each meshing possibilities was relatively low, which is good for analysis. This good state of sensitivity of the buckle may be the result of the mass of our prototype. However, if we reduce the mass, the negative payoff would be having non-uniform meshing capabilities. This was one of the design factors we took into consideration. It's important to also highlight that since our node and element amounts do not change between center and 5 dimension, the von Mises stress analysis and factor of safety between the two can be considered the same as well. From the gathered simulation, you can see that the minimum von Mises stresses vary in the range between a minimum of 8.26 times 10 to the 5th pascals to 5.68 times 10 to the 8th pascals. Within this range, we can compare the 3 hand-calculated sections max stress values. Upon comparison, it is clear that the hand calculations do correlate to what the FEA simulation presents. The figure to the right verifies our factor of safety to be equal to 1.5 plus or minus 0.05, which is dependent to the allocated mesh.
After comparing both FEA and hand calculations, we considered some points of interest that affect the buckle stress and several parts of the prototype. After further analysis, we concluded that both have a maximum point in the square fillet towards the upper part of the section of the buckle, along the inner edge where the strap goes. As you can see in the figure to the right, the buckle is demonstrated to have the maximum point right at the top right corner where it's labeled. We also observed that the maximum that the FEA determines its exact point because it is computer aided. However, in our hand calculations, we were only able to determine in what section the max stress will actually occur because the calculations only allowed for that. After further analysis of both the FEA and hand calculations, we were able to determine that there were some factors that actually differed between both of them. We found out that the buckles differed in weight as well as a factor of safety. One of the reasons we believe that there are irregularities was because of human errors. For example, our factor of safety was much more higher than our hand calculated one by 5.8%, as well as our weight, which came out to be 13% much heavier than the one we were actually achieved using SolidWorks program. We believe that in the case of the weight, it could have been due to the human error because the buckle's filleted sections and its volumes can be very difficult to calculate, thus leading to our hand calculations to be a bit bigger than the program's data. On the other hand, we compared the maximum stresses and concluded that in fact they were similar and had the same point of interest, whereas the max stress is located on both the hand calculations and the FEA simulation. Within the 3 hand calculated sections, the stresses found in FEA simulations held a degree of similarity when compared with one another. Our group decided to begin the project with the FEA simulator as advised due to the fact that we weren't introduced to these calculations prior to the project. Therefore, the calculations resulted being very difficult to compare. Another issue we encountered was the weight of the buckle, but we were able to understand this adversity and at the same time were able to comprehend how we could have corrected our buckle stated in slide 9.